Yiming Chen from Stanford who will tell us about Fortuity and chaos of BPS states.
Okay, thanks for inviting me here. So today I will be talking about the recent paper that I wrote with colleagues at Stanford, Henry Lin and Steven Schenker. I also hope to cover part of the ongoing work with Yiming Chang, Big Sun Xia, and Zhenlin Yang from Tsinghua in China. Okay, so let me start with some motivation. We know that generic high-energy states of a horizontal system are due to black holes. So this is a very universal picture, but it apparently breaks down if we focus on high-energy states that also preserve supersymmetry, namely the BPS states. As an example, we can consider, for example, the Fortuity theory, which we will study also later in the talk. Now, this theory has a lot of supersymmetries, and depending on how many supersymmetries the states preserve, you can divide it into various different BPS sectors. Let's say 1/2 BPS sector, which preserves half the supersymmetry, 1/4 BPS sector, 1/8, etc. And in all these cases, the only known bulk solutions are in fact horizonless solutions that are the so-called Lin-Lunin-Mopasina type geometries, no matter how high the energy is. On the other hand, for the 1/16 BPS sector, the corresponding bulk solution is the supersymmetric black holes, macroscopic black holes with a big horizon. So there seems to be these different choices, and I want to emphasize that the separation is not always as clear as simply the number of supersymmetries. So in N4 case, it seems that you can just divide them based on the number of supersymmetries. But in many examples, especially that people pursue actively in the FASTBall program, the horizonless geometries many times have the same supersymmetry as the supersymmetry black holes. So it's a little bit confusing and has led to a lot of debate on how to interpret this result. Now let me just...
Yiming, just to be clear, if I take like the charge of like a half BPS sector, but then add a bit of mass above the extremal bound, so I'm looking at like neo-extremal, there's some black hole solution, right? It just has a horizon area that goes to 0 as you take the look.
So there you have some non-BPS states that are black holes, but as you go towards the BPS bound, you should have a transition from horizon-full geometry to horizon-less geometry. In general, it's not well understood how that transition happens. Okay, now there's these different choices, and let me give you two possible interpretations of these. Now, one possible opinion is that, well, BPS states are just too special. Their energies are completely fixed by the charges based on the BPS condition, which in particular imply that these states do not exhibit random nature statistics. Okay. One might say that therefore a traditional wisdom about black holes, that black holes are highly chaotic quantum systems, just does not apply in this particular setup. And we should just simply ignore these exceptions of horizonless geometries and maybe move on to more generic context. This is one possible opinion. A second opinion that is completely opposite is that by seeing that there are these different choices, you might conclude there simply is no sharp border between the horizonless geometries and supersymmetric black holes. You might say the horizons are just our inability to understand the microstate in gravity to some detail. Now, one might claim that one can potentially replace the black hole picture by finding even larger families of horizonless geometries, or perhaps more speculatively more general quantum FASTBall pictures. So this opinion says that there already is no sharp line in between the two cases. Okay. Now, I think that recent development in this related direction have suggested corrections to both these opinions. So none of them are correct. And instead, I would claim that the following picture seems to emerge. The first point is that BPS states can in fact be chaotic. And I hope that after the talk today, you will agree that some BPS states at least are as chaotic as generic non-BPS states. I will present some argument why that is true. On the other hand, there does exist a sharp distinction between horizonless geometries and black holes. So one of the sharp distinctions is that they exhibit disparate amount of chaos. The horizonless geometries only exhibit weak chaos, which I will define in more detail later, while the black holes, supersymmetric black holes, they exhibit strong chaos. Another sharp distinction is related to this recent development that people discovered a classification of BPS states into two types, the so-called monotone BPS states and fortuitous BPS states. And the goal of the talk today is to explain the relation of this classification to the property about chaos for these states.
Sorry,
Yes.
Yiming, regarding the option B and the
previous
problem
one.
with the second point,
Yeah.
could it just be that eventually that they'll find some horizonless geometries that also exhibit chaotic behavior?
But I think the claim is that you have to be completely different from all the trustworthy horizonless geometries that have been constructed so far. And all the geometries that have been constructed so far, as I will explain, correspond to this monotone type of BPS states, and they exhibit weak chaos. Now you might say that there might be some sort of horizonless pictures that replace black holes, but
Well, they construct non-BPS horizonless geometries too. I don't know, we can debate whether they're trustworthy constructions or not. And they claim that the energy spectrum of those non-BPS states is also chaotic.
okay, then I will maybe ask whether, let's say, if you look at the spectral form factor, how long is the Thouless time? Whether it's order 1 like a black hole, or maybe very, very long, order n. That would be a distinct feature from the chaos that we will expect for black holes. Certainly, I don't think that people manage to find horizonless geometries that in the non-BPS sector that mimic the strong chaos that we will expect for a black hole. But we can maybe talk more about that later. Are there other questions? Okay. Now let me start by reviewing what we mean by chaos. Right? Let's try to make this concept sharper. One thing we might mean, as Luca was referring to, is the so-called, I would say, eigenvalue chaos. So let's say you have some spectrum of your quantum mechanical system. You have these non-BPS states, which are generally non-degenerate. You also have some degenerate subspace of BPS states. Now, for the non-BPS states, you can just look at their eigenvalues and look at whether the eigenvalues satisfy random matrix universality. Okay? So this is the so-called random matrix statistics of energy levels. But that does not apply for BPS states because all the states have exactly the same energy. On the other hand, there's a different notion of chaos related but distinct, that is the so-called eigenvector chaos, which says that the eigenstates, the wave functions, they resemble random vectors. Now, when we say random vectors, we mean with respect to some simple operators. For example, we expect a generic high-energy microstate to behave like random vectors, which can be made more precise by looking at the so-called eigenstate thermalization hypothesis. Namely, if we consider a simple operator O, and look at its matrix element between two energy eigenstates EI and EJ. The claim is that up to a smooth term, that is just some smooth function of the energy, it should roughly behave like a random matrix. So there are some noisy term that is denoted by Rij here, some off-diagonal noisy term that resembles the property of a random matrix. Now this notion, one can apply this for the BPS states with a small modification. So the idea is that here, since we have a large degenerate subspace of wave functions, instead of looking at the matrix element between two particular eigenstates, we can just project the simple operator O in your theory into the BPS subspace. So here I'm denoting some projection operator P BPS as the projection operator into the subspace. So you conjugate operator O by P BPS, and I will denote that by O hat. By O hat. Now, from the eigenstate thermalization hypothesis, we will expect if the BPS subspace are governed by the same eigenvector chaos, the projected operator should essentially look like a random matrix. Therefore, this was proposed by Lin, Maldacena, Rosenberg, and Chen as a criterion to see whether the BPS subspace is chaotic or not. We say that the BPS subspace is chaotic if and only if this projected operator shows random matrix behavior. Okay. Using this concept, we can in fact turn this question into the eigenvalue chaos of the projected operator. Because to test whether OHEP shows random matrix behavior or not, we can just diagonalize it and look at its spectrum.
Sorry, maybe this is a little bit technical, but here, like, it's still used to KT, so the projector is basically just the infinite time evolution, right?
Here, this is not specific to X2.
Yeah, I'm just asking, like, if you have, say, higher dimensions and you really have a black hole,
Yes.
do you have any idea, like, how to write on this P explicitly?
Well, you can also use the idea of an infinite evolution, but the Hamiltonian would be, for example, the scaling dimension minus the R charge.
Okay.
So that, if you evolve that by a long time, it projects you into the corresponding BPS sector.
Sorry, is this condition for any orbital or just exists orbital?
Okay, very good question. So one would expect that if the BPS subspace, well, later I will discuss different kind of BPS subspace, but I think the conclusion is that if the BPS subspace is strongly chaotic, as for a black hole, you would expect for any choice of single operator, you should find that the projecting operator shows strong chaos, as I will define later. But let's say the BPS subspace, if it's not very chaotic, then the property might depend on which single operator you choose. They might either be totally integrable or a little bit chaotic. In fact, we see these kind of examples in these subspaces that correspond to horizonless geometry. Then the property of this projecting operator will depend on which operator you choose.
Single operator just means, for example, local operator.
Yeah, local operator that, for example, in SYK, that is built out of order 1 number of fermions. I will define it in the H liter context later. Okay? All right. Now, as I said, a simple way to tell whether the projecting operator exhibits random matrix statistics is to look at the nearest neighbor spacing in the spectrum. So this is the most naive way to tell whether it's a random matrix or not. So you look at the difference between these adjacent eigenvalues. Now it's well known that there are two different universality class. In the chaotic system, when this operator is chaotic, you expect a phenomenon that is called the level repulsion between adjacent eigenvalues. That basically means that if you plot the distribution of these SIs, you should find that it has very small probability of two eigenvalues become very close together. So the distribution is the so-called Wigner surmise that starts out at 0, grows, and then decays. On the other hand, for integrable or non-chaotic operators, there doesn't exist this kind of repulsion between eigenvalues. So generically, one finds that the distribution takes a completely different form. It starts out large and then decays. That's the Poisson distribution. Now, it turns out that this only looking at the nearest neighbor spacing is not enough to distinguish, let's say, horizonless geometries from horizon-fold geometries. Because the level spacing only probes the existence of chaos at the finest possible scale. You are only looking at basically the level repulsion between adjacent eigenvalues. On the other hand, one can further quantify the quality of chaos by looking at how far this level repulsion propagates in the spectrum. So let's say there is an effective repulsion between eigenvalues that differ by some energy scale. That I would call that is called the Thouless energy scale in the literature. If the Thouless energy scale is large, that corresponds to very strong chaos. Then the level repulsion propagates a very long distance. A convenient way to look at that is to look at the so-called spectral form vector, which is basically some analytic continuation of the partition function. And In a weakly chaotic system and a strongly chaotic system, the spectral form factor takes a very different form. So this Thouless energy scale, namely the level repulsion energy scale, translates into a time scale that is usually called the Thouless time or REM time in the spectral form factor. In a weakly chaotic system, after the initial decay of the spectral form factor, there is a long period of non-universal part of the spectral form factor. Until it is dominated by this universal level repulsion. So only after a time of order n to some power, the spectral form factor exhibits this REM behavior, this linear growth behavior. On the other hand, in a strongly chaotic system, let's say for a matrix that you draw from a random matrix example, this REM starts out at already order 1 time. So immediately after the initial decay, spectral form factor grows linear.
So are there simple semi-classical examples of both of these things? Like it replace n by h bar maybe in some semi-classical, like, some Billiard ball thing or whatever. Like,
yes, so for example, you can consider a gas of weakly interacting graviton. So
yeah.
In those cases, you expect that the Thouless time is very long. Basically, it's inversely proportional to the interaction strength of the graviton. That would be because the graviton only interacts weakly. So in that case, you would expect the Thouless time that scales inversely as the Newton's constant. On the other hand, for black holes, so here I'm just talking about generic non-BPS black holes. If you look at the spectral form factor, there are these arguments. First, I heard it from Chen Yang, and also you can follow some discussion of my paper with Victor, Ivo, and Juan. We showed that the Thouless time for a generic non-BPS black hole is order 1. Because basically there you can argue what controls the deviation from the REM are the quasi-normal modes, frequencies. And those are order 1. So you go to linear REM at some very early time. So those are some examples not related to BPS that we know how the Thouless time should look like. Here is a generalization of that for this projected object.
Is the energy a number of particles or the inverse space dimension?
Yeah, so here, exactly here I'm not being very clear. So here I imagine doing these calculations in some large n theory. So n, basically you should think of it as related to the Newton's constant or the interacting strength in the box. All right. Now, I hope this makes the criterion clear. So we are using this projective operator, look at this spectrum, see the Thouless time to diagnose chaos. Now with this criterion set, clearly we can ask what we expect. Okay. Now for supersymmetric black holes with ADS2 throat, it was understood that the JT or Schwarzian effective description actually suggests strong chaos. Yes?
I have a question about the previous.
Okay.
So this is basically a question of how fast this sort of leading behavior decays.
No, it's not.
Understand.
So the initial decay, if you choose some, so in the spectral form factor story, so usually you take 0 beta plus IT. But the better thing to study is this spectral form factor with Gaussian filter. So you focus on some particular energy window.
Okay.
If you do that, the initial decay is always very fast. It decays to very small, order 1 time. The story is there are some non-universal feature for weakly chaotic systems.
Oh, I see. So this is the Thouless versus the.
Yeah. Okay. Now for supersymmetric black holes, LMRS did this calculation of this projective operator. And they showed by computing various moments and the spectral form factor of this projective operator using the Schwarzian description, and argued that it exhibits strong chaos. So not only it has a REM, the REM time is order 1. So here I'm just showing some pictures from their paper, which you might recognize what they probably mean. Okay, but here we want to ask, what about the horizon-less geometries? Now, I will later go into detail of these solutions, but just intuitively, the horizonless geometries appear highly structured, at least those geometries that we have well control over. They are usually parameterized by smooth profile of supergravity excitations. So these geometries are usually parameterized by a bunch of functions that correspond to excitation of supergravity fields. Now, I want you to think about supergravity excitations as basically the simple operators in a gravity theory. So when we excite a graviton, we mean some simple operator in the theory. So if these solutions are captured by smooth profile of supergravity excitations, it means that their wave function have very large support along these simple directions. And of course, I'm being a bit vague here, but later we will make this more precise. So this is to say that you don't expect them to be generic random vectors like the wave function of a black hole. And for that reason, intuitively, one might expect them to exhibit less chaos compared to the black holes. Now, to make this more precise, we look at some specific examples, in particularly in Fortuity theory. This was done in the paper with Henry Lin and Steven Schenker. We set out to verify this intuition in concrete examples of horizonless geometries. Now, in the Fortuity theory, what we studied are the 1/2 and 1/4 BPS sectors. Both are described by horizonless geometries. Now, since in this work, we are only able to do the calculation in the weak coupling perturbation theory of the boundary theory. But we expect that this n scaling of the Thouless time to be already visible at weak tooth coupling. So it's already, we expect already to tell the difference, even though it's a weak coupling perturbation theory. Now, in the next few slides, I will tell you some technical detail of what the kind of calculation that we do. But the conclusion, the upshot is essentially that, actually to our surprise, that if you do this exercise, horizonless geometries also exhibit chaos. So they are not totally not chaotic. On the other hand, indeed, this highly structured nature, in fact, allows us to bound the Thouless time. And we can argue that their Thouless time scale as some power in n. So it's only weak chaos.
Sorry, 2 questions about the weak coupling limit. So first, you're doing it, I guess, because it's treatable?
It's treatable, yes.
Okay, and the other question is, why do you expect that it doesn't affect at all the Thouless time?
So maybe let me give you an analogy. So forget about BPS, consider the Lyapunov exponent. So we know it should depend on the tooth coupling. But we expect it as a function of the tooth coupling is always order 1, does not depend on n. So here we expect a similar effect here. The precise value of the Thouless time might be a function of the tooth coupling. But whether it's order 1 or order n to some power, we don't think it depends on the value of the tooth coupling.
You're going to find the Thouless time that scales with them?
Scales with, yeah, or the horizonless geometries. Yes.
And that assumption, like, can you test it in, say, the 1/16 case where you would have had black holes?
No, I'll comment that later. Okay, so now in the next few slides, I'll tell you a little bit about the kind of analysis that we do. I won't go into too much detail. Now, the first case that is simplest is the 1/2 BPS sector. Now, the analysis is basically 2-step. You first want to find the BPS states, then you do this projection, and then look at the spectrum. Now, to find the BPS states, we know that in gauge theories with adjoint matter, a basis for the Hilbert space of states, or via the state operator correspondence, a basis for the operators, are just gauge invariant words built out of letters. And 1/2 BPS sector is particularly simple in this regard. It's basically all the multi-trace operators formed by just one vector, a complex scalar field Z. Okay, denoted by Z here. So for example, you can have trace Z12, trace Z cubed times trace Z5, so you can have many traces product together. Another simplification in this 1/2 BPS sector is that these states, there are BPS in the free theory, there are also BPS in the interacting theory. In other words, these states, they do not develop anomalous dimensions as you turn on the interaction. Okay? So the step of constructing the BPS states is very simple. It's just these multi-traces. Okay, the next step is we want to find out what the projection of a single operator in the gauge theory is, which means that basically we need to know how to compute these kind of matrix elements. So the cat state is some multi-trace of z's, the bra state is some charge conjugate, some multi-trace of z bar, and you have some single operator. Now the problem here is that the complication here is that we are interested in the regime, the energy scale as n squared, so some very, very high energy states. So in this regime, the multi-trace bases are actually highly redundant due to an effect called the trace relations. So here, trace relations come in as just a technical difficulty, but later in the talk it will play a more important role. But let me just show you an example. Let's say you consider E equals to 3, namely you take 3 z's. So with 3 z's in a UN gauge theory, you can form 3 different operators: trace zq, trace z squared times trace z, and trace the cube of the third power of trace z. Okay, you have 3 operators. Now these 3 operators, they are linearly independent when n is greater than 3. However, when n becomes smaller or equal to 3, there exists a linear relation that relates these 3 operators, which means that when you decrease n, this basis now becomes redundant. It's an over-complete basis for the Hilbert space. This causes some difficulty in trying to compute this kind of matrix. Well, if you compute this matrix element, you have to deal with the fact these cat vectors, they are not orthogonal. Now, in the 1/2 BPS sector, there is a single way to solve this problem, which is well known. That is, there is a so-called fermion description of the 1/2 BPS states, which removes this redundancy. The idea is that you can rewrite a 1/2 BPS state in terms of the state of n fermions in a harmonic potential. So we have some one-dimensional harmonic potential here. You have these different levels with energy equal to n plus 1/2, and we put n fermions in this harmonic potential. Okay? So here I'm just writing the Hamiltonian in terms of the creation annihilation operator of the fermions. Now, let me just tell you how to map a half BPS states to this fermion language. So the ADS vacuum, namely the identity operator in the CFT, is mapped to the Fermi C state. So you just put the n fermions on the lowest n levels. That is the ADS vacuum state. Now, we can ask, what is the state corresponding to a single trace operator, trace z to the k? What that does is basically excites the fermion by k units of energy. So you can actually write that down in terms of the fermion operators. Ignore this coefficient. It's just you annihilate a fermion at the L's level and put it back at L plus K level. Okay. So we can successively multiply these multi-trace operators that generate more and more excited states in this fermion language. And there's one-to-one correspondence between these. Well, because of this over-completeness, there's actually a more-to-one map from these traces to a state in the fermion language. Different horizonless geometries corresponds to different ways to excite these fermions. Some of you might know this drop-dead picture for this Ling-Luning-Monosina geometry, and it has a nice interpretation in this fermion language.
And the energy for the fermions is like charge?
Yes, the energy above this vacuum state is the R charge, which also is equal to the scaling dimension, because here we are focusing on the BPS states. Now good. Okay, so now we consider a subspace of fermions with the same energy of order n squared. So we consider some very, very highly excited BPS states. And what that means is that on average, each fermion will have n fermions. So each fermion will have energy of order n. So those are some highly excited states in this harmonic potential. Okay. Now, after we describe the Hilbert space, we want to study this projection of single operators. Given a single operator O in the gauge theory, we want to ask what it looks like after we project it into the half BPS sector. In particular, what it looks like when we express it in terms of these fermion operators. Now, what are the single operators O you can choose in the gauge theory? Here I'm listing some simple choices. For example, you could choose O to be a product of these so-called graviton operators. So here is an example that is a bound state of two gravitons, trace z bar squared times trace z squared. You could do choose some more generic simple operator, let's say some single trace operator or multi-trace operator. It doesn't matter. What matters is that it contains order 1 many letters. Okay? You can have many different ordering of these z bars and z's in the trace. Now you might ask, why am I here restricting to only z's? Well, in the gauge theory, I can put many other letters in the operator. The point is that here we're only doing a calculation at the weak coupling limit in the gauge theory. And many other letters, let's say you put some other scalar field x and y, they simply do not contract with the cat state or the bra state. So it basically doesn't affect the calculation if you consider more general operators. So that's the reason here we just focus on the letters that actually contract with the cat state and the bra state.
Sorry, so this is only valid at small lambda?
Yeah, this is only valid at small lambda. Because when we evaluate this matrix element, we will use the inner product or propagator in the free theory.
But the statement that the half BPS sector is generated by traces of z to the
That
square,
is actually for n lambda, yes.
And that's just because there isn't anything that can mix with them?
Yes.
Like, in theory, you could imagine some other things get light at some finite coupling and then some weird stuff happens. Like some other stuff becomes BPS or like, and then like, this would be very weird, but
Yeah,
yeah.
not to my knowledge.
Yeah.
So could that like some index?
I guess-
Yeah, basically we're just assuming that these things give the index and we're assuming that
That's right, yes.
nothing else joins.
That's right. Okay, and generically, so here we want to project. So here let me discuss the projecting this as a multi-trace operator with many z's and z bars in the trace into the BPS subspace. And okay, and one can show that here. I'm not going to tell you the derivation, but what you can show is that the projected matrix basically involves an order 1 number of moves. Well, each move shifts the energy of a fermion by an order 1 amount. Okay? So for example, is there questions that I can help?
Yeah, it's okay.
Alright. So here, if you look at this this product of two traces, it basically boils down to two moves. So this operator, if you write down an explicit form in terms of the fermions, this trace z squared moves one fermion by 2 units. This trace z bar squared moves another fermion lower it by 2 units. Okay? And in this case, for this operator, you can actually solve the spectrum precisely, and you find the spectrum has large degeneracies. It's not even close to a random matrix. On the other hand, it's true that for more generic operator of this type, the projective operator actually exhibits random matrix statistics if you look at the nearest neighbor spacing. So we are kind of confused about that for a while, but we realize that it's some very weakly chaotic matrix because, as I said, the projective operator only is an order 1 number of moves. Well, it shifts each fermion by an order 1 number of energy. That means that it will actually be bended if we order the states based on some features. Here I'm not discussing the details of how you order them, but basically the idea is that since all the fermions are very highly excited with very large energy, if you just move a few fermions by some order 1 amount, it barely changes the shape of the distribution of the fermions. So that means if you order the states in some smart way, then by acting the matrix on a state, you're not going to get very far away. Okay? And that means that the projective operator is a banded matrix in the sense that it only has non-zero matrix elements in a narrow band along the diagonal. In this case, you can estimate how large that band would be. And so here, we can compute the ratio of this width and the total size of the matrix. And that in the large n limit scales as 1 over n to some weird power, 3 halves. Okay? And in the random matrix literature, it is known that such operators, even when it's chaotic, for example, if you just consider a random matrix but within this band, it has a very, very long Thouless time. A Thouless time that scale as inversely as the square of this number. So here it would Thouless time would be n to the n at least n cubed. Okay.
But this is some like basis, like dependent thing. Like in what basis are we looking at?
The bandedness is basis dependent. You need to order the states in some smart way to see the bandedness. But the Thouless time is basis independent because that will just compute from the spectrum of this operator. That doesn't matter like what basis we write that operator in.
Is there some stupid way to see this? Like you need n to some very high power to like make all the matrix elements non-zero?
Yeah, so you need to add the single operator many, many times to change this state significantly.
Yeah. But why is it like the width squared?
Oh, so here there is a picture. So here, in this work particularly, they think of these matrices as the Hawking matrix in some disordered lattice. And basically they say that if it is random, the propagation is kind of diffusion. So you need time of order and like, but basically it becomes actually chaotic when this width spread over the entire system. That's
so you get some little ballistic tail that will populate all the matrix elements after t to the n
That's right.
3 over 2, but for like them to really get filled out, it's diffusive. So.
Yeah, that's right.
Okay.
That's
Cool.
right. Okay, so about the time. So in the quarter BPS sector, I will be more brief. Basically, in the free theory, it's not very different. So in the free theory, the BPS subspace, the difference is that it is spanned by multi-traces with 2 letters, z and x. Okay, so you can have many ordering z and x in the traces. Now, the analysis in the quarter BPS sector is actually much more involved because different from the half BPS sector that is easy to find BPS states in the interacting theory. Here, not all of these states are BPS in the interacting theory. In fact, most of them will develop anomalous dimension. This is because even at one loop, there is a non-trivial one loop problem to solve. The Hamiltonian is non-zero at one loop. It takes its following form, which I won't go into the detail. This is a fascinating problem to study in its own right because basically I think this is the simplest chaotic matrix model. Chaotic matrix model that contains, well, you need more than one matrix basically to have chaos. And this is basically the simplest kind of such models. And another reason is the infinite n limit of this theory is famously known to be integral. So this theory actually has different limits that sort of incorporate integrability with chaos. It's very interesting. We are instead interested in studying it in the chaotic regime. So when energy is equal to n squared, this model is chaotic. Now, just one way to approach this problem is just to study it numerically. So the degenerate perturbation theory, then we start from this BPS states in the free theory, and we perturb it by looking at one loop problem. It can be studied numerically. So here I'm showing you a plot of SU4 gauge theory, and consider all the states with 14 z's and 7 x's. So some very high excited states compared to n is equal to 4. Now you find this kind of spectrum. So here, horizontal axis is the anomalous dimension of whether the state is lifted. So there are these states with exact 0 energies. They are not lifted. So those will be the BPS states in the one loop theory. But most of the states are lifted. They develop some non-zero anomalous dimension. So there are some distribution of them. And one feature that was studied in this nice paper in the literature is that you can check that the lifted states are chaotic. So that basically means that these lifted states eventually becomes black holes at strong coupling. And you can see that just by checking the eigenvalue chaos, by looking at the level spacing in this for these lifted states, and it fits with some Wigner surmise of GOE nicely. Okay, but we are mostly interested in the LMRS calculation, namely we want to look at the projection operator spectrum. So here I'm choosing some particular simple operator. I don't have time to explain why we choose this operator. But you can project this single operator into this BPS subspace, okay, and look at the level spacing of the projected operator. It basically looks like a Poisson distribution with some deviation, intermediate deviation, which we expect to go away in the large n. We have some understanding of that. On the other hand, you can compare it with if we project the same operator into finite energy windows. Let's say we can project it into this red band of eigenstates that I denote here. So that's some highly excited states in this one loop problem. And if you look at the level spacing of projected operator in that window, you find this linear distribution. Okay, and sort of as you go from non-BPS to BPS, there is a chaotic to non-chaotic transition. The chaos sort of slows down as you go to the BPS subspace. Now here we found a Poisson distribution for this particular operator. We do expect for more generic simple operators, as we saw already in the HEP-QIS sector, we expect some weak chaos. We use the coherent state representation of the quarter BPS states in our paper to sketch an argument why the Thouless time will nonetheless be very, very long. So the chaos is very weak. Thouless time, we think, still grows as NQ, at least as NQ in large n. Now, just as a side comment, in this sector, we can see that there is a slowdown of chaos as we go from non-BPS to BPS. This is a bit similar in spirit to the discussion of black hole string transition, because there you also have some geometry with a horizon transit into a geometry without a horizon. Here, we don't fully understand what the gravity picture of this transition is. But I want to point to you this interesting talk by Shiraz Binwala this year at Strings, which I think proposed the picture of how this transition happens. We have some more comments in our paper. Now let me go to the 116 BPS sector. Now we've presented evidence that the BPS space in the half and quarter BPS sectors are only weakly chaotic. We expect the 1/8 BPS sector to be similar. From the Schwarzen discussion, if it is indeed correct, we should expect to find strong chaos in the 116 BPS sector. Okay. Now, a puzzle is the following. So if you just naively look at the gauge theory calculation, the weak coupling perturbation theory of the 116 BPS sector looks superficially similar to the 1/4 sector. The only difference you can see superficially is that you have a lot more letters. Instead of just X and Z, you have some fermions. But the Hamiltonian still looks kind of similar. It's quartic in the letters. So it's different from, let's say, in SYK, we know that quadratic SYK is very different from quartic SYK. Here, you don't see that very easily. Okay. So the question is, how does the difference arise if indeed the 116 case is dramatically different? It is technically difficult to study this perturbation theory directly, although there are many interesting recent work on that. But I think the current technique is still a little bit far away from computing this LMRS spectrum. However, in the next part of the talk, I will tell you that there is this recent discovery of the fortuity phenomenon that suggests a hint why the 116 BPS sector is qualitatively different. Now, this part of the talk is based on many interesting work in the last couple of years. Particularly is motivated by this nice paper by Pedro Vieira et al. And another paper by Yiming and Yiming this year. Okay, let me give you a lightning review of what this concept of fortuity means. So the idea is that in N-4 theory, there's a sharp, mathematically rigorous idea to classify BPS states into two types. Okay? This classification arises by studying the N-4 at different value of n, or different rank of the gauge group. From the bulk point of view, it means we are trying to think about the bulk theory with different strengths of the gravitational coupling G Newton. Now, the reason we can sort of have a coherent picture on the theory with different n is because there exists this nice basis for the states that are these multi-trace bases that I mentioned earlier. For example, we can look at this operator trace z squared. We can interpret it as an operator in n equals to 100 theory. We can also think of it as an operator in n equals to 10,000 theory. Okay, it makes sense. And in this particular case, we know it's a BPS states for all the possible n's. Now this in fact is the first type of BPS operators. They are the BPS operators no matter what the value of n is. So here I'm drawing a plot that the vertical axis is the difference of the energy from the BPS bound. The horizontal axis is n. Now, similar like this trace z square operator, it is monotone in that it is BPS for arbitrary value of n. Now, at n equals to infinity, all the BPS states are light graviton excitations. Okay. When we say light, we'll always mean comparing the energy to n. And since n is infinity, they are by definition light. I like to think of them as little pieces of Lego. Okay. So there are some very simple graviton excitations that you can write up. Now, as you follow n, when n is small, when you compare the energy with n, they become very heavy objects. Okay, and there are this sort of you assemble these Legos together to form some very heavy object. Those are the horizonless geometries, at least in all the cases that we know in this theory. So it's conjectured that the monotone type operators correspond to all the horizonless geometries. These include the 1/2 BPS, 1/4 BPS, and all the non-1/8 BPS bulk solutions. On the other hand, there exists a different kind of BPS operators that they are only BPS when n becomes small enough. So if you follow these states, they are non-BPS when n is large, but at some critical value of n, they become BPS, and after that, they remain BPS for a smaller value of n. Okay. So how could this happen? A mechanism.
What happens if we just take n all the way to like 1? They just merge into one another or something?
Yeah. So they become BPS, but eventually they become null states.
Yeah.
Right. So that's because of these trace relations.
Yeah.
Now, the reason that this happens is also because of trace relations, but for a different reason. Because here, basically, to find the BPS operator, or before that, to find the Q cohomology, the cohomology of BPS states, we want to find state operators that are satisfied equation QO equals to 0. Q is the supercharge. Now, these operators are basically those that Q acting on O is not manifestly 0. It's some expression in terms of these multi-traces. But it belongs to this family of traces that are the trace relations, such that as you take n to be small, eventually this QO equals to 0. Okay? So they satisfy this equation QO equals to 0 only when n becomes small enough. And n equals to infinity, because these states have non-zero anomalous dimension, they are made out of a mixture of string operators and supergravity excitations. So they kind of are a little bit different, even at infinite n. They contain these strings and stuff. Now, it's understood from index calculation that almost all the states in the 1/16 BPS sector are of this type. They are these fortuitous operators. So here I'm just drawing as a black hole that almost all the microstates of the black hole are these fortuitous type operators. Okay, so what does this have to do with chaos? Now the connection to the chaos is the following. Here I'm drawing the same plot, but I'm also drawing the non-BPS states, other than the BPS states. In the sectors without fortuitous operators, for example, the 1/2, 1/4 BPS sector, as you follow n, the gap never closes as we follow n. Namely, all these non-BPS states, they remain non-BPS. They don't go into the BPS sector. So in this case, it's conceivable that the BPS subspace can retain their distinct features from these non-BPS states, which we expect to be generic non-BPS states. They are chaotic, they are black holes. Okay. And this is not a proof that these states won't get chaotic, but at least this suggests that they are possible that they can retain distinct features. And that's indeed what we see in these explicit examples. Now, this is completely different in sectors dominated by fortuitous operators, for example, in the 116 BPS sector. Here, the gap closes when n becomes small, in particular when the energies of order n squared, because that's the regime where the trace relations are prevalent. And that means that the BPS subspace loses its independence against the invasion of all these non-BPS states. So all these non-BPS crab, they are highly chaotic states. They just go into the BPS subspace. And even though their scaling dimension are fixed once they go into the BPS subspace, but the eigenvector chaos remains. So the BPS subspace retains inherits this eigenvector chaos from these non-BPS states. But emphasize that at the time they enter the BPS subspace, there are already some black hole states in the bulk. Okay? Because E is order n squared. Now this is a picture that suggests why qualitative difference exists in the 116 BPS sector. In the N24 Sylvian-Niels theory, it's hard to, well, there are some progress in this paper by Pedro et al., but in general, it's a little bit hard to flesh out this picture in detail. So in the last part of the talk, I want to tell you a toy model that you can actually see this invasion in very explicit. So before I go there, are there any questions about this part of the talk?
Sorry, so in larger limit, will all the BPS states become non-BPS or not?
So it's known that, for example, in the 116 sector, there are a few number of monotone operators as well. So there are a small number of BPS states remain BPS.
Maybe just to make clear, this plot is plotted for fixed charge and fixed energy.
The fixed charge, yes.
Yeah, and that energy, that's the dotted line, is also fixed.
Yes,
Emily,
yes,
yeah.
yes.
So is there a quantitative definition of what does dominant by fortuitous operator mean?
Yeah, so that means when you count, so you consider energy scale as n squared. At this regime, you can do a Lagrangian analysis of the index and see how many states there are. And the number of states is much greater than what would be. Well, you can imagine if there are no these states coming in, you can count how many states there will be. And that is much smaller than the index. It's exponentially suppressed. It's not just by some prefactor. Okay. And in fact, that is a puzzle in the past, and people seem to find that you can't construct enough BPS states to account for the index. Only after this is discovered, people realize.
Can you get some intuition for why higher amounts of supersymmetry restricts the existence of fortuitous states?
Good. I can give you some partial answer, but that would take me too long. Maybe I'll tell you later.
Okay.
I want to tell you a little bit more about this toy model of Fortuity and chaos invasion. Now, the toy model is not something we've never seen. So this is work with Yiming, Lip-Sun, Xia, and Zhenbin Yang. We are studying basically SYK-like models that also exhibit monotones and fortuitous states. Now, we study various kinds of models, but in this talk, let me just expand the simplest possible case, the Manila n equals to 2 supersymmetric SYK model that was discussed by these authors. Now, this is a model with n complex fermions. These are the anti-commutation relation. And here I'm writing down the supercharge Q, which isCijk times psi I, psi j, psi k. Okay? I'd like you to think about the supercharge at least abstractly as a 3 form. So this C is a totally anasymmetric tensor with 3 indices, as 3 form. And the Hamiltonian is just the square of the supercharge. Now, what is the Hilbert space of this model? Now, we can separate the states into states with different R charge. There is a fault vacuum 0. It's not the state with lowest energy, but it's the state that doesn't contain any fermion that has R charge 0. the fermion number 1 state, number 2 state, R charge equals to 2, etc. Okay. Now in this model, an arbitrary state with R charge k can be written as the following. So it's some coefficient times these k fermions. And I want you to think of it abstractly as a k form, because again, you can write this coefficient as a totally antisymmetric tensor with k indices. It's totally antisymmetric because all the fermions, they anti-compute. Now, let's think about the Q action, Q acting on an operator. So that can be easily understood in language of forms as the wedge product of a 3-form C with OK, O sub k. So start with O sub k and act with Q, it takes you to a k plus 3 form. Okay. Now comes the important point. If you fix k, fix the number of fermions or fix the R charge, and let's consider very, very large n. Generically, we never expect solutions to this Q closed equation. There are no solutions to C wedge OK to 0. The reason is the following. We can count the number of variables and compare it with the number of equations here. The number of variables in this equation are the number of independent components of a K form, while here, actually the number of equations corresponds to the number of components of a K plus 3 form. Okay? So when n is very large, if you look at the number of K form as a function of K, it grows. And if you start with a K form, the number of equations is much larger than the number of unknowns. You don't have solutions. But that tells you that there are no Q-closed operators, and therefore no BPS states with fixed R charge K and large n. Now you can ask why we do have some BPS states in X2 SYK, how do they happen? Okay, the observation is that we in fact start to have solutions to this equation when n is decreased until it reaches n is roughly 2k. The reason is that in a finite n theory, if you look at the number of k form as a function of k, it first increases until you reach n over 2, and then it decreases to 0. Okay? So if I start out here, then I increase k by 3, I still have more equations than unknowns, so I don't get BPS states here. But if I start out here at L3, I actually decrease the number of components. So I start to have Q-closed operators. So this will suggest that, well, we should expect all the BPS states to be here, to the right of this point. Okay? And in fact, so if you think a little bit more, there are also no BPS states here, because all the Q-closed operators here are already Q-exact. So you can write all the OK, also K here as Q acting on some K minus 3 form operator. Okay? And the BPS states are basically Q-closed mod Q-exact. So in the end, it tells you only for these 3 particular charges you get BPS states. Now, remarkably, this feature was predicted correctly from the Schwarzian effective theory, which are agnostic about this kind of argument, this random coupling argument. But let's say if you open up Stanford Wheaton, you find that they indeed find correctly that in this case, there are only these 3 special R charge that have BPS states. Here we reinterpreted this discussion as saying that all the BPS states here are fortuitous, meaning that if you consider these BPS states and increase n, they must become non-BPS. They're large n, they are not BPS operators. Okay. Now, let me just show you an example of following n and this effect of chaos invasion in this toy model. So here, I'm just taking some specific value of n and k. Let's say n equals to 12. For the green ones, they are the sectors, charge sectors that have BPS states. They're basically in this picture, the middle one, since n is 12, middle one is 6. So you have BPS states when k is equal to 5, 6, and 7. You don't have BPS states when k is equal to 3 and 4. When n is equal to 10, you have BPS states when k is equal to 4, 5, and 6. You don't have BPS states otherwise. Okay? Now, in all these cases, the spectrum is gapped. So when you have BPS states, you just have these BPS states, and then you have a gap, and here you have the non-BPS states. When you don't have BPS states, you just simply have a gap. Okay. I didn't discuss the case of odd n. So when n is odd, the situation is a little bit different. You have, for example, when n is 11, you have BPS states when k is equal to 5 and 6. You don't have BPS states otherwise, but there are two special charge sectors that are gapless. So when k is equal to 4, this sector is gapless, and also for k is equal to 7. That means that there are many, many low-lying states, exponentially close to zero energy, but no exact BPS states.
So if k equals 7, it's just fortuitous phenomenon happening the other way in n.
Yeah, so I didn't discuss that. So in this model, you can think about Q for Q monotone. You can also think about Q dagger monotone. A fortuitous states is one that is neither Q monotone nor Q dagger monotone. So indeed, all these green ones are fortuitous. In this model, there are no monotone operators with generic coupling C. Okay. So
But they also
maybe-
don't become null, they exit again, right?
yes.
So they become BPS, they're there for a bit, and then they exit again.
They can become non-BPS, they can also become null states. So there are two possibilities.
In fact, there's always a gap. List one.
Yeah,
Yes, they're becoming.
yes, so that's right. So the gap indeed seems to say, so you can maybe ask just here, so how does it happen, right? How does this non-BPS states invade? Like there's a gap in between. Now here, in particular, in this model, that's what I'm going to show, is that this gapless sector helps. So what happens is the following. Let me just focus on k equals to 4. As we said, when n is equal to 12, there are no BPS states and there is a gap. So that in this picture corresponds to this part here. But there are no low-lying states, and these are the spectrum. There are many exciting states with a gap. Here I'm interpolating the model from n to 12 to n to 11 just by a very stupid way, by decoupling the last fermion, adiabatically tuning those coupling to 0. And as we see here, indeed, the gap closes, so it becomes gapless when n equals to 11. All these states, they become very, very light, very close to the BPS bound. Here, the gap is exponentially small, but there are no exact BPS operators. That's the first step. And the second step is that when we go from this n equals to 11 to n equals to 10, what happens is that these non-BPS states now invade the BPS sector. They become exactly BPS when n is equal to 10. And at the same time, a gap opens up again. So this, as you can see, that on this side there is a gap again. Okay? So in this model, you can see explicitly this kind of invasion phenomenon happen. You can understand many things about these states. For example, you can follow each of these states and try to see whether the eigenvector chaos disappear or not, etc. Okay. So the conclusion is that indeed these states carry their chaos into the BPS subspace, as we sketched in our paper with Stephen. Okay, let me summarize.
Sorry, that's a conclusion that you reached by doing numerics?
In this case,
yeah.
yes, you
Okay,
can check
like you
it.
just checked explicitly that the spectrum is chaotic for all these values of n. Well, for n equal 10, where you do have BPS state.
Well, here it's just n equals 2 SYK, so we already know that, right? For integer n. Here, maybe more something new that we can check is to follow a wave function of some particular microstate as a function, continuous function of n, and see, for example, many properties like entanglement entropy. Here we can try to compute the entanglement entropy of this state. Let's say you separate the fermion into two parts, compute the entanglement entropy, and see whether it remains unchanged. So in this model, we only have fortuitous states, so everything is very chaotic. But as I will comment later about model with monotones. Let me summarize. Okay, let's revisit the claims that I made at the beginning, and just to point out that how we understand them. So as I said, BPS states can indeed be chaotic. By chaotic, we mean these LMRS chaos. This is some sharp criterion for what we mean by chaos in the BPS sector. And some BPS states are as chaotic as generic non-BPS states. Through this invasion mechanism, it really doesn't make sense to distinguish them anymore after these non-BPS states enter the BPS subspace. So they are sort of have the same property. There is a sharp distinction between the horizon-less geometries and black holes. They exhibit a very different amount of chaos. And I talked about how to quantify that. We quantify that by looking at how the Thouless time scale as n. And this is further explained by a classification, or supported by a classification as these monotone and fortuitous type operators. Now, along this line, I think there are still many interesting questions to ask. I think one technical question that would certainly, I think one should do it recently is, so try to test this LMRS criterion directly in the 116 BPS sector. I think the current technique is almost close to the stage that we can actually see a large family of these supersymmetric black hole microstates that's in your computer. So that's an interesting question to explore. Now, another direction is to test this LMRS criteria for more complex microstate geometries, such that as the superstrata or perhaps these non-BPS kind of solutions that Luca mentioned, how much they can really mimic the chaos that we expect for a black hole. For example, you might ask, does the amount of chaos increase as this road gets deeper, as it resembles AES2 more and more? Okay, what's the limit there? I think the answer is still not entirely clear in this question. Now, more on the toy model. So we are currently studying a class of SYK models in which they are both monotone and fortuitous states. You can, I hope this will come out in a month or two. So the idea is, so here you need to be slightly more careful because SYK model is a little bit different from, well, it's somewhat different from traditional holography theory in that its large N limit is not very nice. If you take the large N limit, there are order n many light fields in the bulk. So in this model, it's easy to find kind of bad monotones, these monotones that do not have very nice large N limit. But we identified the class of models that have monotones that are sort of like graviton operators in n equals to 4. And in that case, you can really see a big distinction between fortuitous and monotone operators. An interesting question we are thinking about here is whether you can find G sigma solutions that correspond to horizonless geometries. Some large N solutions that are not conformal, but preserve some amount of supersymmetry. There's some hope that maybe we can do that, but I'm not sure.
So, by both you mean comparable?
No, not comparable. So in the model we study fortuitous states, they are exponentially many. Monotone states, they grow polynomially in n.
Yeah, that was the case also for Sept.
So in there, the n scaling is a little bit different. It's like it's not really polynomial versus. It's like.
But both work there.
The fortuitous ones was always dominating.
Yeah, but it's monotone was also there.
Yeah, in the super Yiming's case, there are also a few number of monotones in the 116 set. Yes.
So what's the difference here?
Oh no, here we are trying to study some toy models that help us to explore this sort of invasion ideas, etc.
Okay, so it's not the new phenomenon.
Not a new phenomenon, just a toy model for the phenomenon that we expect in N4. So that is related to this first point that is also interesting to directly study N4, but technically that's hard.
Is there any argument that if fortuitous states exist at all, they have to dominate? Like that, so physically we think if there's a black hole solution, it's the dominant one. But like...
Yeah, I don't think we understand this supersymmetry. We don't understand this lifting effect. So when you increase n, sort of this black hole becomes smaller and smaller. Eventually it becomes maybe Planck size, and suddenly it should become non-BPS. We don't understand that.
Sorry, should it actually become smaller? Isn't it just like individual states are being left? Oh,
Okay.
like the total number of states,
Yeah.
fortuitous states, is always growing with n, right? It's just individual ones. Like, yeah, I don't know.
Sorry.
I don't know how you'd even dial that. You'd have to like.
No, fortuitous decreases with a fixed charge.
Yeah, so there's a distinction between a fixed charge and extended infinity. Then the number of fortuitous states should go to 0.
Yes.
I think what you might be thinking of is if you scale Q with alpha n squared, then the number grows.
Yeah.
So
Yeah.
the bulk picture of this is mysterious. I don't think anybody knows what happens to these black holes. Suddenly, originally it's BPS, but now it becomes non-BPS.
So what's the scaling of entropy? Because the G Newton goes to big, A over 14 Newton, and A is fixed by charge, just
A is fixed by charge.
right? So G Newton goes big, they can say, okay, entropy becomes small. So the things have to be from,
So if you're really holding the charge fixed, I think the area is going to get smaller with n, right? Just the classical black hole solution, the area will get smaller. Wait, what is? Yeah, what is the classical black hole solution do?
So you fix the charge and decrease the Newton's constant.
Yeah, but that fix the charge in units of. Yes, it's like,
That leaves the entropy invariant, right? The entropy is just pi q squared.
Right.
true.
And then area divided by G Newton. G Newton gets smaller, area gets also gets smaller.
so that seems to be saying there's more fortuitous states.
Why does it say
Increasing
that?
n and fixing q. I mean, if the area of the classical black hole is getting bigger, or area before G is getting bigger, and these fortuitous states are supposed to be counting the black hole entropy, then they should behave the same way, right?
No. I guess there you imagine also taking Q to scale with n. There are two things you can do.
Yes, so I'm saying what happens to the classical black hole if you hold Q like actually fixed while making Q? So is it?
And then I think it should get smaller as you have.
I thought you were saying grabbing.
Well, I was saying that in the flat space case it
There's
stays
different
constant.
scalings of Q, right?
In the flat space case it stays constant.
Yeah.
Because it's pi q
Yeah.
squared.
Yeah.
In ADS, I suspect it gets smaller, but I have to look at the formula.
But it should just be the 10D. It should be like 10D flat space black hole at some point, right? So is it just it stays constant and then it becomes stringy at some point? Or like, there should be something that can be understood. Like there should be some signature of the breakdown of the semi-classical black hole. We're taking G to become weak, so like, is it just like a black hole string transition? Like, I don't know.
You mean which is string scale, like black hole?
I mean, okay, we have this 10D black hole. I think we agree that the area classically is just, it's in Planck units is like pi, some power of q to the 8, I would guess.
So that's
There's
fixed.
something, and that's just staying constant. So it seems like you have a constant number of states as you're dialing in and holding q fixed. But then at some point, Q Newton gets really small. Sorry, at some point, like the coupling is getting really weak, so the string scale gets big in Planck units, and so you'll get a black hole string transition. Is that the fortuitous state stopping doing BPS? Or?
But I don't see. I don't see why it implies this. They become non-BPS. You might imagine it becomes something.
Yeah. So maybe it becomes stringy, but then once it's stringy, there's no reason the entropy needs to stay constant, and somehow. I don't know. It'd be nice to see a calculation where the entropy gets smaller at large n, if that's what's meant to be happening.
I guess at some point there's no reason to trust the semi-classical solution, right? Once
We'd like a weakly coupled string answer or something, right? hole, it's Fortuity, something, you know.
Sorry, but when n is very big, Planck length is very small.
Yeah, but the black hole will stay fixed sized in Planck units. Like the area of a quite Austrian black hole is like pi q squared in Planck units. Area of 4G is pi q squared.
But here we care about number of states, right? Which is dimensionless.
Yeah,
Pi q
so
squared is
Planck
dimensionless.
units like
Pi q squared is
the number.
dimensionless. E to the pi q squared would be the number, right?
Yeah. I'm just thinking about like A over 4G.
Yeah, so if you work in Planck units, then G is 1, area is 4 pi q squared, then the quarter that's the pi q squared.
But the string exchanges in that mapping
Well,
become not black hole. It's smaller than state.
is it not that there's... Okay, at least when the black hole is very classical looking, then it's like, if you increase n, some fortuitous states like go up, but then simultaneously, like some stop being null and like appear. I mean, that's what's happening in n equals 2 SYK, right? It's like...
Sorry, can you say that part again? So some go up and...
Some stop being BPS, but at the same time there's things that are fortuitous states that like stop being null. Right, as you make n smaller, then some fortuitous states arrive and other fortuitous states become null, and it keeps the entropy roughly constant. Is that the right story?
Yes, that's right.
Okay, so we don't actually expect this. So the number of states stays constant.
So like in this plot, like there are these two effects, right? I need to go back, but like as new states come in, old states become null. So
Yeah.
one effect, I think the becoming null effect actually wins over the new state coming in. So eventually, as you go to n very small, there are no states there.
But that very large n, what Jeff said is not true, right? At infinite n, strictly infinite n, there are no fortuitous states.
There are no fortuitous states.
Yeah.
But at that point, it won't be a black hole anymore, right? There'll be some scale where it just stops being a black hole, and then
That's right. Yes. Yeah, but I do think this mechanism. I haven't thought it through, but this mechanism I don't think is understood.
Sorry, I got confused why you were concerned about the gap in SYK at all. Because the gap is a semi-classical feature, right?
What do you mean I'm concerned about it?
Well, you were, maybe I'm misremembering, but the reason you were happy, in this transition was that you passed from, I forgot what it was, no BPS with a gap to BPS with a gap to, sorry, how was it? What was the top one?
The top one is no BPS state with a gap.
Yes, and the middle one is BPS state.
The middle one is no BPS state.
Gapless.
Yes.
Okay.
Well, I'm not concerned about it. I'm just saying it's nice that there's some intermediate end interpolate between this limit and this limit. Okay.
But my only point is, once we see fortuitous states lifting, right, in your earlier plots.
So lifting is here.
Yeah. Well, like there. Shouldn't we expect that that's precisely the point at which the semi-classical description of the black hole is not trustworthy anymore?
No, so yeah, that's a good point. Here is actually perfectly trustworthy, right?
Well, it looks trustworthy on the plot, but...
No, I mean, so here is just around this point, where you have these BPS states. It's at least at n equals to 10, it's perfectly, I mean, so here is finite n, but if you take the large n limit, here is described by the Schwarzian theory.
Well, maybe I'm thinking about the case of n equal 4 superring nodes.
Yeah, I
So there, when you fix the charge and you increase n, eventually you see these fortuitous states lifting. And I thought we agreed that this fortuitous states lifting is precisely corresponds to the moment when the semi-classical description of the black hole becomes non-reliable, and you have to add that stringy corrections become large, right? That's why the
That seems to
Smarts
follow
get.
from what we said, yes.
So I'm asking here when n is equal to 10. Yeah, exactly at 10.
Yeah,
when we
here-
see the things lifting, shouldn't we apply the same logic and say that the semi-classical description is not good?
Here I don't really see. It seems a little bit different from n equals to 4, as far as I can tell.
I see.
Maybe you can ask, one question one can ask is, in this SYK story, how to understand this lifting from the AES2 picture. I'm not sure.
Is it for the fixed charge, even for super young, if you choose n correctly, or whatever, do you have like exponential states? Like n equals n?
Sorry, in n equals to 4 or in SYK?
Not if n equals 4, do you have a similar phenomenon of this exponential like state?
Oh, you mean this? I don't think so. That is part of the one paper by Luca et al. Right? So you study the Schwarzian spectrum in N24. In that case, you don't find gaps.
But I think that's because we don't know what happens at fixed Q and values of n where the spectrum of fortuitous states just starts lifting, right? Because at those values, the analysis that I did with math and people should fail, right? It should be stringy corrections that control the density of states.
Okay, I see. But at least when you take charge to scale as n squared and take the larger limit, you don't find
Yes,
gaps.
yes.
Here in SYK, even if you take the similar limit, you take r charge to scale as n and take the larger limit, you have this special.
I'm serious.
You have this special gap sections. So that seems to be different. Although, even in n equals 4, if you actually do this following n business, it's a little bit subtle maybe for non-integer n. I don't know what happens. Maybe one can answer that. Okay, so let me just end with the last slide. So this slide is just some general comment. So I think it's well appreciated that many of the puzzles in quantum gravity seem to revolve around the existence of large number of null states in the semi-classical gravity theory. I would like to say that these are likely related to the trace relations in the X4 sigma mules. These are intricate, non-perturbative relations that cut down the number of states at infinity n. So infinity n Hilbert space is the semi-classical bulk theory, and at finite n there are these relations that cut down the number of states. So in the past, this was only understood when the trace relations are somewhat light. For example, there are these interesting stories involving giant graviton brains, etc., that have to do with trace relations. Now, I find it interesting that this fortuity phenomena is an example where very heavy trace relations are critical for the existence of the supersymmetric black holes. So that's the reason that I think this is very interesting. So with that, I'd like to thank you for your attention.
Any more questions for Yiming?
The physical picture for this like BPS scales. I mean, we know that the Newton of exponents once they have the scrambling as a physical picture, but here I'm a little bit confused. Like, what would be the picture, especially for this half BPS weakly chaos?
Well, there, the physical picture, I will interpret it as saying that if you, let's say, percube the metric a little bit. So the half BPS, one picture is you have these dual giant graviton brains.
Yeah.
N of them in AES space-time at different radial coordinate. It's not a very nice picture, but it's roughly the picture. I will interpret it as saying you're sending some gravitational wave with some single
but here it's like all the states have the same energy, right?
Yes, so you have that corresponds to different ways of arranging these brains.
Okay.
So the picture is roughly that the simple operators only change the position of these branes a little bit. It's not enough to move you from like one state in the subspace to a completely different state in the subspace.
Okay.
That is not true for, apparently that is not true for black holes. All the states are sort of random states. So there isn't like a locality in the BPS subspace. The some states are closer than other states. In the black hole case, it's all kind of random.
Okay.
That's like the physical picture.
Okay.
Yes.
So you reviewed these two types of chaos at the beginning of the talk, this eigenvalue chaos versus eigenvector chaos. Which type do you think is analogous to the chaos you are defining for the BPS?
Oh, it's eigenvector chaos. Because we are using this generalization of the eigenstate normalization hypothesis of looking at the matrix element or the projection of a simple operator in these states.
Yeah, the statement about the behavior of the matrix element seems to be very different from the normal ETH. Like normal ETH is saying this matrix element is roughly a Gaussian random matrix.
Roughly is important. It's
But
approximately.
here you are looking at the spectrum for that.
Yeah, here I'm basically looking at by looking at the spectrum, testing whether the matrix element corresponds to a random matrix or not. So eigenvalue chaos here is just a way of testing the eigenvector chaos. It's basically confusing.
I see.
The point being, if you take any operator and project it into a random subspace, then it will become a random subspace in that.
Yeah.
You project up your random operator and then you have eigenvalue.
Yeah. There is a nice paper by Schrennicki on studying this random projection.
So I think for general operator projection, the BPS sector, like you won't get like literally a semicircle. Like you'll get eigenvalue repulsion, you'll maybe get a square root edge or something, I'm not completely certain, but it definitely won't be. Semicircle is specific to like large mass, like free thing.
Yeah.
So what does that say about the eigenvectors? Anything?
Not obviously, because I think the effect would be just like a random matrix with some potential.
Yeah, but
it's not
if we
random.
want to think of that as coming from some, I don't know, it's like some, morally like a Pauli operator or something projected into some like random subspace, then like what property of the random subspace makes it?
I think it's higher moments. The
Yes.
eigenvectors, like
The low moments are not given
by weak contractions.
Yeah. But like how do we rephrase that in terms of the subspace? Like if this is all meant to be really statements about the subspace and the operator is just some shit that we're using to break that. Maybe it's still just random and it's just the operator is like weird in some way. I'm not sure. Maybe the statement is only about if you project an operator around random subspace. The statement is only about eigenvalue repulsion.
I think the shape of the spectrum certainly depends on the operator.
Schrennicki's statement was not about semicircle,
It's
right?
about repulsion.
I thought it was about eigenvalue repulsion. No?
Yes, he doesn't find a perfect semicircle.
Okay.
Yeah.
What paper of this is this?
I don't remember the title. It's cited in the
Nicky eigenvector chaos.
I don't remember the title. But he take the thing he considered is basically P1, P2, P1. So the single operator that he project is also a projection operator. But it's just two independent random projection operators. And he found some interesting story. The spectrum is also not a perfect semicircle. It's some particular distribution.
All right, let's
So
thank.
there's the question.
Yeah, but potentially very naive question, but should we think about black hole remnants as like as an example of these horizonless geometries?
I don't know what about the black hole remnants.
Like
my answer is no.
they're a sort of hypothetical thing, right? Like that probably doesn't exist. But
Naive answer is no. First of all, I don't personally think.
But these BPS states are kind of like remnants. They survive forever, right? And APS.
No.
But they don't have large. They don't have large entropy. They could have large entanglement entropy between them.
But remnant is over Wittgenstein.
Well, it depends how you define it. So, yeah.
I like to think of them as like galaxy with stars.
Okay, let's thank you.